Hey guys, tonight we're slipping into the hidden workshops of ancient Rome, where engineers solve problems that would make modern contractors weep with envy. Forget the gladiators and emperors for a moment. Forget the marble statues and political intrigue. Tonight, we're following the real magicians of Rome, the men who made water flow uphill, who mixed concrete that grew stronger with age, who built roads that refused to die. You've probably driven on a highway that needed repaving after 15 years. The Romans built roads that are still carrying traffic after 2000. You've seen concrete crumble after a few decades of weathering. Roman concrete sits underwater, actually getting harder, laughing at the centuries. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And down in the comments, tell me where you're listening from and what time it is where you are. I love knowing this community spans the globe, all of us drifting off together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. We begin with water. Rome needed water the way modern cities need electricity. Millions of people crammed into a city that sat on 7 hills, far from any major river that could sustain them. The Tiber was there, sure, but it was sluggish and seasonal, often more mud than water by late summer. So Roman engineers looked at the mountains. 40 miles away, in the Apennine foothills, springs bubbled up pure and cold. The problem was obvious. How do you move millions of gallons of water across valleys, over hills, through solid rock, without pumps? Because here's the thing, Romans didn't have pumps. Not in the way we think of them. No steam power, no electricity, no mechanical advantage beyond human muscle and animal strength. What they had was mathematics and patience. The solution was the aqueduct, and it worked on a principle so simple it feels like cheating. Water flows downhill. But the genius was in the execution. Roman engineers would survey a route from mountain spring to city fountain, calculating a gradient so gentle you couldn't see it with your naked eye. 1 foot of drop for every 300 feet of distance. That's a slope of 0.3%. Imagine trying to eyeball that across 40 miles of wilderness. They couldn't. So they invented surveying tools, the groma for right angles, the courbates for level lines, a water level that could detect differences of a fraction of an inch. Then they started building. Sometimes the channel ran on arches, those iconic stone bridges we picture when we think of Roman aqueducts. But most of the time, the channel was invisible. Cut into hillsides, buried in trenches, tunneled through mountains. For miles and miles, water flowed through darkness, following that patient downward slope, never rushing, never stopping. Historians still argue whether Roman engineers understood hydraulic principles theoretically or just knew what worked through trial and error. The mathematics they left behind suggest they understood pressure, flow rate, and gradient with surprising sophistication. But they wrote almost nothing down. The knowledge passed from master to apprentice, demonstrated on site, refined across generations. Here's a curiosity that sounds too strange to be true. Some aqueducts included stretches where water flowed uphill. Not for long, just short sections where an inverted siphon used pressure to push water up the far side of a valley. They'd build a U-shaped pipe of lead or stone, drop water down one side, and watch it climb the other side almost to its original height. Physics borrowed from nature. The same principle that makes a siphon work in your garden hose, scaled up to move water across canyons. By the height of the empire, 11 major aqueducts fed Rome, delivering about 300 gallons per person per day. That's more than most modern American cities provide. Some of that water was wasted. Romans weren't exactly conservation-minded, but the engineering behind it was flawless. Channels that ran for 50 miles, dropping just a few hundred feet, arriving at the city with enough pressure to fill fountains, supply bathhouses, flush sewers, and overflow into the Tiber. All without a single pump. Just gravity, geometry, and patience measured in decades. The concrete that built Rome wasn't like anything you'd recognize today. Modern concrete is strong when it's poured, then slowly weakens as water and weather attack it. Roman concrete did the opposite. It got stronger, especially underwater, where it seemed to feed on seawater, growing denser and more resilient with every passing year. The secret was an accident of geography. Near Naples, there's a place called Pozzuoli, named after the ancient town of Puteoli. Volcanic activity had blessed the region with something special, a type of ash that Romans called pulvis puteolinus. We call it pozzolana. It's formed when volcanic magma hits water and explodes into glass particles, then weathers into a fine, reactive powder. Some Roman engineer, whose name is lost to history, mixed this ash with lime and discovered something miraculous. The resulting concrete didn't just harden, it transformed. When seawater touched it, the lime and volcanic ash underwent a chemical reaction that created crystals of a mineral called aluminum tobermarite. These crystals grew slowly, filling tiny cracks, binding the mixture tighter and tighter over centuries. Modern scientists only figured this out in the last few decades, using electron microscopes to peer into samples taken from ancient harbors. What they found astonished them. 2,000-year-old Roman concrete was still generating new crystals, still strengthening, still defying every principle of material degradation they understood. Meanwhile, modern concrete in seawater starts crumbling within 50 years. The Romans built harbors that are still standing. Massive breakwaters that protected ships from Mediterranean storms. Underwater foundations for bridges and wharves. They'd build wooden forms, fill them with this volcanic concrete mixture, and sink them into position. The concrete would set underwater, something modern concrete can't do without expensive additives and careful engineering. Then it would just sit there, getting stronger, while empires rose and fell above it. Here's where it gets eccentric. Romans sometimes mixed broken pottery into their concrete. Shards of amphoras, fragments of roof tiles, crushed brick. Historians still argue whether this was just using cheap filler material or if they understood that fired clay added certain properties to the mix. Recent analysis suggests the pottery shards prevented cracks from spreading, acting like primitive rebar. The bits of clay would stop a stress fracture in its tracks, dispersing the force throughout the structure. Accidental genius or intentional engineering? We'll never know for certain. The recipe wasn't exactly secret, but it wasn't written down in detail either. Vitruvius, the Roman architect who left us the most complete technical manual from antiquity, mentions pozzolana and describes mixing ratios. But he writes like someone explaining cooking to people who already know how to cook. Take volcanic ash, mix with lime, add aggregate. The proportions, the technique, the subtle adjustments for different applications, all of that lived in the hands of the workers, passed down through demonstration. When the Western Empire collapsed, the knowledge went with it. Medieval builders tried to replicate Roman concrete and failed. They'd mix lime and sand and whatever volcanic ash they could find, but the results were inferior. Something was missing from their understanding. It wasn't until the 18th century that engineers began to rediscover hydraulic cement, and even then, they didn't match Roman durability. Modern Portland cement is stronger initially, but it can't touch Roman concrete for longevity. We've built dams and harbors that will need replacement within a century. Roman harbors at Caesarea and Portus laugh at the waves after 2 millennia. There's something almost melancholy about it. We've gained so much knowledge, developed such sophisticated chemistry and material science, but we've lost the patience for concrete that takes centuries to reach its full strength. We want roads paved in weeks, buildings constructed in months, infrastructure that's functional immediately. The Romans thought in generations. They built for an empire they believed would last forever. And in a way, they were right. The concrete endures, even when the empire doesn't. A Roman road was never just a road. It was a geological sandwich built one careful layer at a time, designed to outlast the empire itself. And it did. If you've ever driven through Europe and noticed a suspiciously straight stretch of highway cutting through winding countryside, there's a good chance you're following a route that Roman surveyors laid out 2,000 years ago. The Via Appia, the Via Flaminia, the Via Aurelia. These weren't paths worn by feet over time. They were deliberate, engineered constructions that involved moving tons of earth and stone. The process started with the surveyors, the same meticulous engineers who built the aqueducts. They'd plot the straightest possible line between 2 points, adjusting only for major obstacles like mountains or rivers. Curves were for the weak. Romans preferred to cut through a hillside rather than go around it. Once the route was marked, the real work began. First, they'd excavate a trench, sometimes 6 feet deep, removing all the soil down to bedrock if possible. This was the foundation, and it had to be absolutely solid. Then came the layers. Each one served a specific purpose, distributing weight in a way that seems almost intuitive once you understand it, but required genuine engineering insight to develop. The bottom layer was large stones, irregular chunks fitted together like a three-dimensional puzzle. This was called the statumen, and it provided a stable base that wouldn't shift or settle. Above that came the rudis, smaller stones and gravel mixed with mortar or clay. This layer absorbed and distributed the pressure from above, preventing any single point of stress from cracking through. Then the nucleus, finer gravel and sand, sometimes mixed with lime to create a kind of concrete layer. This was the load-bearing heart of the road, the engineering that made everything work. Finally, the surface. In important roads near cities, this meant fitted stones, basalt or limestone blocks cut to interlock perfectly, with a slight crown in the center, so rainwater would run off to drainage ditches on either side. These surface stones were the only part visible to travelers, but they were just the top tenth of the structure. The genius was underneath. The way the layers worked together to distribute weight meant that even heavy military wagons, loaded with equipment and supplies, wouldn't damage the road surface. The force spread downward and outward, dissipating through the layers until it reached the stable foundation. Modern highways use essentially the same principle: base layer, subbase, surface course. We just do it with different materials and bigger machines. But the Romans figured it out with shovels and surveying tools. Here's something that sounds impossible, but is documented. Roman military engineers could build a temporary marching road at a rate of 20 miles per day. Not the full multi-layered structure, obviously, but a graded, drained, compacted surface suitable for moving an army. They'd travel with the tools and knowledge, improvising with local materials, creating infrastructure as they conquered. Then, if the territory became permanent, civilian engineers would return and upgrade the temporary road to full specifications. Historians still argue whether the famous Roman straightness was for practical speed or symbolic projection of power. Probably both. A straight road gets you there faster. But it also says Rome doesn't negotiate with geography. Rome imposes its will on the landscape. And there's an eccentric detail that most people miss: milestone markers. Every Roman mile, about 9/10 of our modern mile, they place a stone cylinder marking the distance to Rome. All roads lead to Rome wasn't poetic metaphor. It was literal navigation. Every milestone told you exactly how far you were from the golden milestone in the Forum, the 0 point from which the empire measured itself. Some of these milestones are still standing, still marking distances to a capital that no longer rules anything. The roads themselves have fared remarkably well. Not all of them, certainly. Time and weather and human intervention have destroyed plenty. But walk certain streets in Rome, and you're stepping on the same basalt blocks that Julius Caesar's soldiers marched across. Drive through the English countryside, and you might be following the path of the Fosseway, laid down shortly after the conquest of Britain. The durability wasn't accidental. It came from understanding how forces move through layered materials, how water is the enemy of every road, how proper drainage matters more than surface hardness. Modern roads often fail because water seeps in, freezes, expands, and cracks the pavement from within. Roman roads had drainage channels, crowned surfaces, and layers that shed moisture. They thought about what would happen in winter, in spring floods, across centuries of weather. They built for forever, and sometimes they succeeded. The baths of Caracalla weren't just a place to get clean. They were a machine, a vast, intricate system that moved water and heat with the precision of a Swiss watch, scaled up to serve thousands of people simultaneously. Imagine a building that covers 27 acres. Now imagine that building needs to maintain multiple pools at different temperatures, heat air in dozens of rooms, provide hot and cold running water, and do all of this without electricity, without gas furnaces, without any of the infrastructure we take for granted. That was the challenge Roman engineers solved, and they solved it so well that the baths operated for centuries. The heart of the system was the hypocaust. We'll return to that miracle of physics in detail later tonight. For now, just picture hollow floors supported on small pillars, with furnaces heating air that flowed through those spaces beneath your feet. But the baths were more than just the hypocaust. They required a complete understanding of how water behaves, how heat transfers, how to maintain pressure across a massive distribution network. 6 million liters of water move through the baths of Caracalla every day. That's enough to fill 2 Olympic swimming pools. Every day, the water arrived via aqueduct, entering at the highest point of the complex, so gravity could do most of the distribution work. From there, lead and terracotta pipes branched throughout the structure, feeding the various pools and fountains. The cold pool, the frigidarium, was supplied directly, no heating needed. Mediterranean climate meant cold was relative anyway. The warm pool, the tepidarium, required more sophistication. Water would flow through pipes that passed near, but not directly over, the furnaces, picking up heat gradually. Too much heat would create steam and burst the pipes. Too little meant uncomfortable bathing. The calibration had to be perfect. Then came the hot pool, the caldarium. This was directly above the main furnaces, suspended over the hypocaust at its most intense. Water here could reach temperatures that would cook you if you weren't careful. The Romans loved it. Historians still argue whether the extreme heat preference was cultural machismo, or if Romans genuinely had higher heat tolerance than modern people. Probably cultural. Every society decides what constitutes comfortable bathing temperature, and Romans apparently decided that uncomfortable bordering on dangerous was ideal. But here's where the engineering gets really interesting. Temperature zoning. The baths weren't uniformly heated. Different rooms required different temperatures, and the system had to maintain those differences reliably. The solution was architectural. Rooms that needed more heat were positioned directly above furnace complexes, with larger hypocaust spaces to channel more hot air. Cooler rooms were farther from furnaces, with smaller hypocaust gaps and thicker floors that insulated against excess heat. It was analog computing, using physics instead of electronics to solve a complex problem. And it worked flawlessly. The furnaces themselves ran constantly, fed by enslaved workers who received no mention in the historical record beyond occasional graffiti and archaeological evidence. Tons of wood every day, feeding fires that could never go out. If a furnace went cold, it would take days to bring the entire system back to temperature. So the fires burned, day and night, year after year. Here's an eccentric detail. The Romans sometimes used recycled materials as fuel. Old wooden scaffolding, demolished building materials, even olive pits from the oil presses. Anything that burned contributed to the fires. It was early recycling, driven by the practical need to keep the furnaces fed. The social complexity matched the engineering complexity. Baths weren't just about hygiene. They were recreation centers, meeting places, unofficial business venues. You'd proceed through the rooms in sequence. Exercise in the palestra, sweat in the sudatorium, soak in the caldarium, cool down in the tepidarium, shock your system in the frigidarium. The temperature progression was physiologically intentional. Heat opened your pores, cold closed them. The sequence supposedly purified your body. Whether it actually did anything medically is debatable, but the ritual was sacred, and the engineering made it possible. Without the hypocaust, without the sophisticated water distribution, without the careful architectural planning, the baths would have been just another pool. Instead, they were monuments to Roman technical achievement. Buildings that said, we can control water, we can control fire, we can create comfort and luxury on a scale no other civilization has attempted. The baths of Caracalla stood for centuries, serving the empire until the aqueducts failed and the knowledge to repair them was lost. Even in ruins, they're magnificent. Those massive vaulted ceilings, the empty pools, the elaborate mosaic floors. But what's missing, what you can't see without imagination, is the system. The living, breathing machine that made it all work. That's what the Romans built. Not just monuments, but functional wonders. The Pantheon's dome shouldn't exist. At least, it shouldn't still be standing after 19 centuries of weather, earthquakes, and general neglect. It's the largest unreinforced concrete dome ever built, spanning 143 feet across. Even today, with steel reinforcement and computer modeling, engineers hesitate to attempt something similar. The Romans did it with concrete, patience, and secrets they took to their graves. Stand beneath that dome and look up at the oculus, the circular opening at the top that lets in rain and sunlight. You're looking at a structure that weighs 4,500 tons, all of it pressing outward and downward simultaneously, trying to tear itself apart. It hasn't. The key was making the dome lighter as it rose. At the base, the concrete is thick and dense, made with heavy aggregate, travertine, and brick fragments. As you move upward, the mixture changes. The middle sections use lighter volcanic stones. Near the top, the concrete contains pumice, that foamy volcanic rock that's more air than stone. Some pieces of pumice near the oculus are so light they'd float in water. This gradual lightening reduced the overall weight dramatically, but more importantly, it reduced the stress at the critical points. The base of the dome, where all that weight concentrates, was strong and heavy. The top, where the structure was most vulnerable to collapse, was practically hollow. But weight reduction alone doesn't explain the Pantheon's survival. The dome also contains invisible tension rings. Embedded in the concrete, invisible from inside or outside, are courses of brick that circle the dome at specific heights. These rings act like the steel bands around a wooden barrel, holding everything together under compression. When the dome tries to spread outward under its own weight, these rings resist, keeping the structure stable. Historians still argue whether Roman engineers understood this principle theoretically or discovered it through trial and error. No Roman text explicitly describes the tension ring concept, but the rings are there precisely placed, doing exactly what modern structural engineers would specify. Either Romans understood compression mechanics at a sophisticated level, or they got incredibly lucky multiple times. The oculus adds another layer of complexity. That 9-meter hole at the top removes weight? Yes, but it also creates a structural vulnerability. A dome wants to push outward in all directions equally. Cut a hole in the top, and you've disrupted that equilibrium. The solution was making the oculus rim incredibly thick and rigid, essentially creating a massive compression ring that held its own shape while the rest of the dome pressed against it. Again, no documentation explains this. We reverse engineer the logic from the structure itself. Here's an eccentric detail that sounds absurd. The floor of the Pantheon has drainage holes because rain comes straight through the oculus. Not gutters, not channels, just holes drilled in the marble floor leading to underground drains. The building is designed to accept that it will be rained on internally. That's not a flaw. That's confidence in your drainage engineering. The concrete formula for the Pantheon was probably specific to this building, adjusted for the unique stresses of a massive dome. Vitruvius, remember, wrote his architectural manual just before the Pantheon was built in its current form. Hadrian's reconstruction replaced an earlier building. He describes concrete mixing but doesn't give the precise formula for something this ambitious. The knowledge lived in the hands of the builders, the concretararios who mixed and poured and shaped. When a recipe needed adjusting, lighter aggregate here, different ratio of pozzolana there, they knew. They could feel the mixture, judge its consistency, understand intuitively what modern engineers need computers to calculate. The construction process probably took years. The formwork alone, the wooden structure that held the concrete while it cured, would have been a massive engineering project. A dome-shaped lattice of timber, precisely curved, strong enough to support thousands of tons of wet concrete. They built it from the inside, probably working upward in sections, allowing lower portions to cure while upper sections were poured. The formwork would have filled the entire interior space, a temporary wooden dome inside the permanent concrete one. Then, when the concrete had cured enough to support itself, they disassembled the formwork and carried it out piece by piece. Imagine that moment. The last support removed, the final timber extracted, and the dome just stands, holding itself up through nothing but its own shape and the integrity of its materials. Either it works or it catastrophically doesn't. It worked, and it's still working 2,000 years later, outlasting every other dome built in the ancient world. The Pantheon has survived because Roman engineers understood something fundamental. In architecture, less can be more. The oculus removes weight and creates beauty simultaneously. The pumice aggregate weakens individual sections, but strengthens the whole. The invisible tension rings do their work unseen. It's engineering that doesn't show off. It just endures. Before there were cranes powered by steam or electricity, there were cranes powered by humans walking in circles. Massive wooden structures that could lift 20 tons using nothing but rope, pulleys, and people willing to climb inside a giant wheel and start walking. These machines transformed Roman construction. Without them, the Colosseum would be impossible. The Pantheon would be impossible. Every massive temple, every towering column, every block of marble that sits 30 feet in the air, all of it required lifting, and lifting meant cranes. The basic principle is older than Rome. A simple lever and fulcrum can multiply your strength, letting you lift weights that would be impossible with muscle alone. But Rome took that principle and scaled it up, adding complexity until they had machines that could lift loads weighing as much as a modern pickup truck. The key innovation was the tread wheel. A large wooden wheel, maybe 15 feet in diameter, with steps inside like a hamster wheel. Workers would climb in, anywhere from 2 to 8 people, depending on the wheel's size, and start walking. As they walked, the wheel rotated, winding rope around an axle that was geared to lift the load. The mechanical advantage was significant. 8 men walking could lift a weight that would require 40 men pulling directly. But it wasn't just about strength, it was about control. The wheel could be stopped instantly, held steady while masons positioned a block, then resumed with precision. Try doing that with 40 men on ropes, and you'll understand why the tread wheel was revolutionary. The cranes themselves were engineering marvels of timber construction. Massive beams fitted together with mortise and tenon joints, reinforced with iron brackets. A vertical post served as the main axis, with an angled jib extending outward to provide reach. Ropes ran from the tread wheel through multiple pulleys, sometimes 5 or 6 in series, multiplying the lifting force with each pass. Historians still argue whether Roman engineers understood the mathematical principles of mechanical advantage or just knew empirically that more pulleys meant easier lifting. The absence of detailed technical writings makes it hard to say, but they definitely understood load limits. Inscriptions on some lifting hooks specify maximum weights, suggesting they'd learned through experience, probably catastrophic failure, where the limits were. Here's where it gets eccentric. Some cranes could rotate. Not the whole structure, but the jib could swing in an arc, allowing workers to lift a block from a cart, rotate it over the construction site, and lower it into place without moving the crane base. This required a turntable mechanism at the base, carefully engineered to handle the sideways forces without toppling. The mechanical sophistication rivals anything built before the Industrial Revolution, and they built these machines on site, assembled them for specific projects, then disassembled and moved them. Portable industrial machinery 2,000 years ago. The scale varied dramatically. Small cranes for everyday construction might lift a few hundred pounds. Medium cranes could handle 5 tons. The largest, the ones used for temple columns and triumphal arches, could lift 20 tons or more. That's 40,000 pounds, suspended on wooden beams and rope, positioned with accuracy measured in inches. One mistake, and you've got a multi-ton stone crushing workers and destroying months of preparation. Yet accidents seem to have been relatively rare. Not absent, construction has always been dangerous, but rare enough that they don't dominate the historical record. That speaks to the skill of the operators. The people inside the tread wheels weren't just muscle. They needed rhythm, coordination, the ability to respond instantly to signals from the ground crew. Speed up, slow down, stop, hold. All communicated through shouts and hand signals while walking inside a rotating wheel. It's like conducting an orchestra where the instruments are human bodies and the music is tons of stone rising into the air. The ropes themselves were another marvel. Made from hemp or flax, twisted into cables that could withstand enormous tension without snapping. Roman rope making was sophisticated enough to create lines strong enough for cranes, but flexible enough to run through pulleys smoothly. Too stiff and the rope won't bend properly. Too weak and it snaps under load. They found the balance through centuries of incremental improvement. When we look at Roman buildings today, we see the stones. We marvel at the precision of fitted blocks, the height of columns, the ambition of the architecture. What we don't see are the machines that made it possible. The cranes have vanished, dismantled and reused, or rotted away across the centuries. But they were there at every construction site, turning human walking into vertical, lifting power. The technology persisted long after Rome fell. Medieval cathedrals used similar treadwheel cranes, building on the Roman foundation. Some of those medieval cranes still exist, preserved inside churches as historical artifacts. But the Roman cranes themselves are gone. We know them from carved reliefs, from brief descriptions in technical manuals, from the buildings they lifted into existence. Ghosts of machines, visible only in what they left behind. Beneath the Colosseum's arena floor was a secret, a vast mechanical underworld called the hypogeum, where elaborate elevator systems transformed theatrical spectacle into something approaching magic. The audience saw lions and bears materialize from nowhere. They saw elaborate stage sets rise into place as if conjured by gods. What they didn't see were the dozens of enslaved workers sweating in darkness, operating the machinery that made Rome's entertainment possible. The hypogeum was a maze of corridors and chambers, 2 stories deep, extending across the entire footprint of the arena. 80 vertical shafts pierced up through what would become the arena floor, each one housing a lifting mechanism. These weren't simple platforms. Some were counterweight elevators, where the weight of descending scenery helped lift the next load. Some used capstan windlasses, where workers pushed horizontal bars in circles to wind rope around a vertical drum. The most sophisticated used a combination of both, achieving lifting speeds that must have seemed miraculous to the audience above. Imagine the coordination required. A naval battle scene ends. Yes, they flooded the arena for mock sea battles in the early years, and needs to transform into a forest for the next act. Below ground, teams at multiple shafts receive signals. They begin lifting simultaneously, timed to the second. Trees emerge from trapdoors. Rocks rise into position. Painted backdrops slide into place. All while gladiators and animals are moving above, and 70,000 spectators watch every moment. One mistimed lift, and you've got colliding scenery, or worse, exposed machinery that breaks the theatrical illusion. The Romans were obsessed with that illusion. The whole point was making the impossible seem effortless, and the hypogeum workers had to be perfect. Historians still argue whether the elevator systems used counterweights or human power exclusively. Archaeological evidence suggests both, deployed strategically based on weight and speed requirements. A small tiger cage might be counterweight, dropping an equivalent weight as it rose. A massive stone platform would need teams of men on capstans, grunting and sweating in synchronization. The noise down there must have been incredible. Shouted commands, creaking rope, wooden wheels groaning under tension, animals snarling in their cages. All of it happening in semi-darkness, lit by oil lamps that added smoke and heat to the already stifling air. And yet the show went on, flawlessly, day after day. Here's an eccentric detail. Some of the animal cages had false floors that would tilt or drop away, forcing the animal forward into the elevator platform without requiring a human to open a gate. Remote mechanical release, operated by a pull rope from a safe distance. The Romans weren't just engineers. They were problem solvers who thought about safety, efficiency, and reliability. Even 2,000 years ago, even in a society built on enslaved labor, someone designed mechanisms to minimize risk. The vertical shafts themselves were architectural achievements, perfectly aligned through 2 underground levels and the arena floor above, lined with brick or stone to prevent collapse. Some included guide rails to keep the elevator platforms stable as they rose. Others used counterweight channels running alongside the main shaft, separated by walls but mechanically connected. The precision required to excavate and build these shafts under an elliptical arena, ensuring they emerged at exactly the right positions on the floor above, suggests sophisticated surveying and spatial planning. One misaligned shaft, and you've got an elevator that can't emerge, or worse, damages the arena floor. The Colosseum was built in less than 10 years. That includes excavating the hypogeum, installing 80 elevator shafts, constructing the seating for 70,000 people, and finishing the exterior facade. The organization and coordination required staggers the mind. Thousands of workers, hundreds of specialized craftsmen, all working to precise specifications. And when it was finished, when the inaugural games began, the machinery performed. For 400 years, the hypogeum operated. Through countless games, spectacles, executions, and entertainments, the elevators lifted. The mechanisms wore out and were replaced, ropes frayed and were renewed, but the system functioned. When we visit the Colosseum today, the hypogeum is exposed. The arena floor is gone, destroyed or removed centuries ago, leaving the mechanical guts visible under open sky. You can walk through those corridors, see the shaft openings, trace the pathways that animals and gladiators followed from holding cells to death or glory. But you can't see it working. You can't watch a platform rise smoothly into position, can't hear the coordinated shouts of the workers below, can't experience the shock of a lion appearing from nowhere on the arena floor. That machinery is silent now. The ropes have rotted, the wooden mechanisms decayed, the knowledge of operation lost. What remains is the architecture of possibility. The proof that Romans could build theatrical machinery sophisticated enough to fool an entire stadium. They understood showmanship, they understood engineering, and they understood that the best magic is the kind where you never see how it's done. The hypogeum kept that secret for centuries. Roman plumbing was a triumph of engineering wrapped around a slow-acting poison. Every major city had water flowing through networks of lead pipes, stamped with imperial seals to prevent theft and ensure quality control. The Latin word for lead was plumbum. That's where we get plumber and plumbing. It's also where Romans got a lifetime of low-level lead exposure that may have contributed to cognitive decline, fertility issues, and a host of health problems they never connected to their water system. The irony is dense enough to taste. Romans built the most sophisticated water distribution network in the ancient world, bringing clean mountain spring water across miles of aqueducts, only to poison it in the last 100 feet before consumption. Lead was everywhere in Roman life. Not just pipes, but cooking vessels, wine cups, cosmetics, even as a sweetener in food. They'd boil grape must in lead pots to create sapa, a syrup used to sweeten wine and preserve food. The lead leached into the liquid, creating lead acetate, which has a sweet taste. Sugar of lead, they called it. Delicious and deadly. But the pipes were the constant exposure. Every sip of water from a public fountain, every bath, every cooking pot filled from the household tap potentially carried dissolved lead. The concentration varied based on water chemistry. Soft, acidic water leached more lead than hard, alkaline water. Rome's water, coming from limestone springs, was relatively hard, which probably saved them from worse effects. But relatively hard doesn't mean safe. Modern analysis of Roman bones shows lead levels significantly higher than pre-industrial populations. Not high enough for acute poisoning, but elevated enough to cause subtle, chronic effects. Historians still argue whether lead poisoning contributed to Rome's decline. Some point to the cognitive effects of lead exposure: impaired judgment, increased aggression, reduced impulse control, and suggest that an entire ruling class suffering from mild lead toxicity might make poor decisions. Others note that correlation isn't causation, and plenty of other factors explain Rome's eventual fragmentation. The debate continues, civilized and academic, while the lead pipes remain as archaeological evidence of a choice that seemed perfectly reasonable at the time. Here's the thing: Romans knew lead could be dangerous. Vitruvius, writing in the 1st century BCE, explicitly warned against lead pipes. He noted that workers in lead foundries had terrible health, pale complexions, and shortened lifespans. He recommended using terracotta pipes instead, claiming water tasted better and was healthier. So the knowledge was there. Some Romans chose terracotta. But lead was easier to work with, more durable, less likely to crack, and could be formed into complex joins and angles that terracotta couldn't match. It was a practical choice, an engineering decision that prioritized functionality over health warnings that seemed abstract and uncertain. How many times have humans made that exact choice? The pipes themselves were manufactured with impressive precision. Sheets of lead were cast, then rolled around wooden forms to create cylinders. The seams were soldered, with more lead, naturally, creating watertight joints. Different diameters for different purposes, all standardized across the empire. A plumber in Britain used the same gauge pipes as a plumber in Syria. That standardization, that empire-wide uniformity, is a hallmark of Roman engineering. But it also meant empire-wide lead exposure. The pipes were stamped with imperial marks indicating the manufacturer, the diameter, and sometimes the property owner. These stamps survive, pressed into the lead, legible after 2,000 years. Some are museums now, artifacts of both engineering achievement and public health failure. An eccentric detail: wealthy Romans sometimes used silver pipes for drinking water, believing them healthier and more prestigious. They were right about healthier accidentally. Silver doesn't leach into water the way lead does, and it even has mild antimicrobial properties. But this wasn't universal knowledge. It was status signaling that happened to be medically beneficial. The poor got lead. The rich got silver. Both thought they were just choosing based on aesthetics and cost. Public fountains, where most Romans got their water, used lead extensively. The fountain basins, the distribution pipes, the spouts, all cast in lead for durability and ease of maintenance. These fountains ran constantly, water flowing continuously to prevent stagnation. The flow-through system probably reduced lead absorption somewhat, fresh water replacing contaminated water constantly. But the contact surface was still lead, and chemistry doesn't care about flow rates. Microscopic amounts dissolved continuously. When the aqueducts failed, and they did eventually fail as the empire fragmented, the pipes became useless. Medieval populations sometimes melted them down for other purposes, recycling the lead for roofing or other construction. Some pipes remained buried, forgotten until modern archaeology uncovered them. Those excavated pipes tell stories through chemical analysis. Lead isotope ratios reveal which mines the lead came from, tracing trade networks across the empire. Corrosion patterns show where water chemistry was aggressive, where it was mild. And lead concentration in nearby soil suggests centuries of slow contamination spreading outward from buried pipes. The Romans engineered water distribution brilliantly. They understood pressure, gravity, and hydraulics. They built systems that functioned reliably across vast distances. But they poisoned themselves, slowly and unknowingly, through a material choice that seemed entirely reasonable. It's a reminder that engineering excellence doesn't guarantee wisdom. Sometimes you can solve the technical problem perfectly and still choose the wrong solution. Roman warfare wasn't just about discipline and tactics. It was about mathematics. When a legion laid siege to a fortified city, engineers would arrive with calculating instruments and centuries of accumulated knowledge about trajectories, tensions, and the breaking points of stone walls. The testudo, the famous tortoise formation where shields overlapped to create a mobile shell, was geometry made flesh. But the real mathematical magic happened with the siege engines. Ballistae and catapults that could throw stones weighing 90 pounds across 300 yards with enough force to shatter masonry. These weren't crude machines built through guesswork. They were precision instruments, designed according to formulas that related projectile weight to spring dimensions, arm length to release angle. The Greeks developed the mathematical foundations. The Romans industrialized them. Every legion had engineers who could construct standard siege weapons from memory, using modular components that could be prefabricated or built on-site from local timber. The key component was the spring mechanism. Early versions used twisted sinew, bundles of animal tendon, or hair wound tight to create torsion. Wooden arms inserted into these bundles could be pulled back, storing energy in the twisted fibers. Release the arms, and the stored energy launched the projectile. Simple in concept, devilishly complex in execution. The tension had to be identical on both sides, or the projectile would veer off course. The twist rate, the bundle diameter, the arm length, all of these had to be calculated precisely for each projectile weight. Roman engineers developed formulas based on the weight of the stone you wanted to throw. If you knew the projectile weight, you could calculate the diameter of the spring bundles, the length of the throwing arms, the size of the frame. These formulas were written down, passed along, refined across generations. Historians still argue whether the Romans understood the underlying physics, energy storage, mechanical advantage, parabolic trajectories, or simply followed empirical rules that worked. Probably somewhere in between. They knew what worked, developed mathematical relationships to describe it, but may not have understood why in terms of modern physics. Does it matter if you understand gravity when you can calculate exactly where your stone will land? The ballista was essentially a giant crossbow, firing large arrows or smaller stones with terrifying accuracy. Two vertical spring bundles, one on each side, powered arms that drew back a bowstring. The projectile sat in a groove, aimed using a simple sight system. Released the trigger, and the string snapped forward, launching the bolt with enough force to punch through shields and armor. Effective range was several hundred yards. Skilled operators could hit man-sized targets at that distance. That's not luck. That's understanding ballistics. The onager was different, a one-armed stone thrower that used a single massive spring bundle. The throwing arm, pulled back against tremendous tension, would slam forward against a padded crossbeam, launching the stone in a high arc. Less accurate than the ballista, but capable of throwing heavier projectiles. The name onager comes from the wild ass because the machine's kick when fired resembled the animal's violent back leg strike. Romans appreciated the comparison enough to make it official nomenclature. Here's an eccentric detail. Some siege engines had adjustable sights, notches or markers that allowed operators to calibrate for distance, compensating for different projectile weights or wind conditions. They were doing battlefield adjustments based on observed results, iterating toward accuracy through rapid trial and error. That's field engineering, conducted under combat conditions, with enemy arrows flying overhead. The Romans also used trebuchets in later periods, though the classic counterweight trebuchet was more a medieval development. Roman versions were typically traction trebuchets, where teams of men pulled ropes to swing the throwing arm. Less powerful than later designs, but still effective for lobbing diseased animal carcasses over walls or throwing burning materials into wooden structures. Psychological warfare wrapped in engineering. The Siege of Masada showcases Roman engineering at its most grimly impressive. Facing a fortress on a plateau with cliffs on all sides, Roman engineers built a massive earthen ramp, hauling millions of tons of earth and stone to create an inclined plane that siege towers could climb. It took months. It was methodical, relentless, and completely unnecessary from a strategic standpoint. They could have just waited for the defenders to run out of supplies. But Rome wanted to demonstrate that no position was unassailable, that Roman engineering could overcome any natural advantage. The ramp still exists, a monument to patient, brutal application of engineering principles to military problems. Testudo formations allowed troops to advance under arrow fire, shields locked overhead and on all sides. But getting the angles right required training and discipline. Shields had to overlap precisely, leaving no gaps while still allowing mobility. Too tight, and the formation couldn't move. Too loose, and arrows found flesh. The Romans drilled endlessly, turning geometry into muscle memory. When we think about Roman military success, we often focus on discipline, training, and tactical flexibility. All true, but underneath was engineering knowledge that turned warfare into applied mathematics. Siege engines that could be standardized and mass-produced, tactics based on geometric formations, fortifications designed using precise measurement and surveying. The legion was as much a mobile engineering corps as a fighting force. They built camps every night, full fortifications with walls, ditches, and gates, all to standardized plans. They built bridges, siege engines, roads, aqueducts. Fighting was almost secondary to the construction work, and when they fought, they did it with machines calibrated to mathematical precision, throwing stones that followed predictable arcs toward calculated targets. Warfare as engineering problem, victory as the solution. Roman military engineers could build a bridge across the Rhine in 10 days. Not a simple pontoon bridge, though they could do those in a day, but a solid timber structure capable of carrying entire legions with their equipment, wagons, and siege engines. Julius Caesar documented one such bridge in his commentaries, describing it with enough detail that modern engineers have reconstructed the design. It was brilliant, a prefabricated marvel that anticipated modern modular construction by 2,000 years. The Rhine was formidable, deep, fast-flowing, prone to floods. Any bridge had to resist tremendous lateral pressure from the current, while supporting vertical loads from thousands of troops. The solution was a framework of driven piles arranged in pairs, angled against each other to form triangular bracing. Picture two heavy timbers, each about a foot thick, driven into the riverbed at opposing angles so they meet underwater. The angle configuration made them incredibly stable against lateral forces. Current pushing from upstream was resisted by the downstream angle of one pile, pushing it tighter against its partner. It was judo applied to hydrology, using the river's force to strengthen the structure. Horizontal beams connected the pile pairs, creating a rigid framework. Then came the roadbed, planks laid across the beams, secured but not permanent. The whole thing could be disassembled when the army was finished, leaving minimal trace. Romans often built bridges just across, then destroyed them to prevent enemy pursuit. Temporary infrastructure as tactical weapon. The speed of construction was the real achievement. 10 days from empty river to functional bridge wide enough for 2 wagons to pass. That required planning, prefabrication, and flawless execution. Timber was cut to standard lengths before arriving at the river. Pile drivers, essentially large hammers lifted by human-powered cranes, drove the foundation piles at predetermined spacing. Survey teams ensured everything aligned perfectly because one misplaced pile could compromise the entire structure. Teams worked simultaneously along the river's length, each group responsible for a section. When one section was complete, they moved downstream to the next. Assembly line construction, military style. Historians still argue whether Roman bridge engineers used mathematical calculations for load distribution or relied on empirical rules refined through experience. Evidence suggests both. They had formulas for pile spacing based on river depth and current speed, but they also adjusted based on what they observed during construction. Practical engineering that adapted to reality rather than rigidly following theory. Here's an eccentric detail. Some bridge designs included upstream barriers, timber frames filled with stones positioned ahead of the main piles to break the current's force. These breakwaters reduce stress on the bridge itself, essentially creating calm water around the structure. It's the same principle modern engineers use with bridge piers, just implemented with wooden cribs and river stones. The Romans weren't inventing hydrodynamics, but they were solving its problems elegantly. Permanent bridges were different challenges entirely. Stone arch bridges required foundations sunk into riverbeds, massive piers that could support the weight of stone arches. The technique involved building cofferdams, watertight enclosures of driven piles and clay. Workers would pump or bail water from inside the cofferdam, creating a dry workspace below the waterline. Then they'd excavate down to bedrock or stable substrate and build the stone pier foundation. It was slow, expensive, and dangerous. Workers drowned when cofferdams failed. Floods destroyed partially completed structures. But the results were spectacular. The Pont du Gard, we'll visit its perfection in detail soon, still stands because those foundations were built to last millennia. Military bridges were temporary by design, but some became permanent through repeated reconstruction. If an army kept crossing at the same location, eventually someone would replace the timber with stone. Tactical infrastructure becoming civilian architecture. The knowledge transfer from military to civilian engineering was constant in Rome. Soldiers trained in bridge construction retired and became civilian contractors. The techniques they'd learned building military crossings applied directly to peacetime projects. Every legionary engineer was potentially a future builder of roads, aqueducts, and bridges. Bridge building manuals probably existed, though none survived complete. Fragments of technical knowledge appear in various sources. Vitruvius mentions bridge foundations. Caesar describes specific designs, but the comprehensive guide is lost. What remains is the bridges themselves and the techniques we can reverse engineer from studying them. The speed of Roman military bridge construction had strategic implications beyond the obvious. An army that could cross a major river in 10 days had mobility that enemies couldn't match. Fortifications meant nothing if Romans could simply bridge past them. Natural barriers became temporary obstacles. That psychological advantage was as important as the physical crossing. Enemies knew Romans could build bridges, had seen it happen, understood the futility of relying on rivers for protection. So they retreated or surrendered rather than waiting behind water they thought was safety. Engineering as warfare. Construction as conquest. A bridge built not just to cross, but to demonstrate that crossing was inevitable. Rest for a moment. Let the image settle. Legionaries working in coordinated teams, massive timbers being lifted into place, the river slowly tamed by human planning and muscle. The sound of hammers, the shouts of foremen, the gradual emergence of order from chaos. Engineering as it was meant to be. Purposeful, powerful, unstoppable. The Cloaca Maxima was built to carry away Rome's shame. Sewage, wastewater, runoff from the streets. Everything Rome wanted to forget flowed through stone tunnels large enough to sail a small boat through. Some of those tunnels are still functioning today, still channeling waste beneath modern Rome, making the Cloaca Maxima one of the world's oldest continuously operating infrastructure systems. It began with the Etruscan kings, before Rome was Rome. The valley between the Capitoline and Palatine hills was marshy, prone to flooding, unusable for construction. So the Etruscans dug a drainage channel, lined it with stone, and covered it over. That modest beginning would eventually grow into a system spanning miles of underground passages, connecting to smaller sewers throughout the city. The main channel was massive, 10 to 11 feet wide in places, tall enough for a man to walk upright. The walls were built from massive stone blocks fitted together without mortar, relying on precision, cutting, and gravity to hold everything in place. An arched roof distributed weight from the buildings and streets above. The engineering was sophisticated enough that the structure survived earthquakes, floods, and 2,000 years of continuous use. The gradient was carefully calculated to ensure flow without creating excessive velocity. Too steep and the current would erode the channel. Too shallow and waste would accumulate, creating blockages and disease. Roman engineers achieved the balance through surveying and experience, creating a slope that moved waste efficiently while preserving the infrastructure. Most of Rome's sewage didn't reach the Cloaca Maxima directly. Smaller sewers branched throughout the city, collecting waste from public latrines, bathhouses, and street drains. These tributaries fed into larger collectors, which eventually connected to the main system. It was hierarchical infrastructure, the sewage equivalent of a river system, with streams feeding into rivers feeding into the main channel. Public latrines were surprisingly social spaces. Stone benches with regularly spaced holes, positioned over flowing water channels. No privacy, no partitions, just rows of Romans conducting business while chatting with neighbors. Modern sensibilities recoil, but Romans saw it as perfectly normal. The constantly flowing water beneath the seats carried waste away immediately, flushing into the sewer system. It was actually more sanitary than many alternatives available at the time. Historians still argue whether wealthy Romans had private toilets connected to sewers or used chamber pots that slaves emptied. Evidence suggests both, depending on the property and its location relative to sewer lines. Connecting to the cloaca maxima required permission and probably fees. Not everyone could afford direct access to Rome's greatest feat of sanitary engineering. Here's an eccentric detail that sounds too bizarre to believe. Sewer gas occasionally exploded in the tunnels. Methane from decomposing waste would accumulate in poorly ventilated sections, and if someone entered with an open flame, torches were the standard lighting, boom. Romans documented these incidents, confused about the cause but aware of the danger. They learned empirically that entering certain sewer sections with flames was deadly, even if they didn't understand combustible gas. The cloaca maxima emptied into the Tiber, which created downstream problems that Romans largely ignored. The river became polluted, particularly downstream of the city where waste accumulated. But out of sight was out of mind, and most Romans got their water from aqueducts bringing fresh mountain springs, not from the Tiber. So the pollution was someone else's problem, specifically the problem of whoever lived downstream. Maintenance was constant and necessary. Blockages had to be cleared, structural damage repaired, sediment removed. Rome employed workers specifically for sewer maintenance, jobs that were probably among the least desirable in the empire. These workers would enter the tunnels, navigate by torchlight through darkness and stench, and clear whatever was blocking flow. Occasionally, they'd find valuable items dropped through street drains, coins, jewelry, anything that might fall through a grate. These discoveries were probably one of the few perks of an otherwise miserable occupation. The system expanded continuously as Rome grew. New neighborhoods meant new sewers, new connections to the main system. By the empire's height, hundreds of miles of sewer tunnels wormed beneath the city. Most were small, barely big enough to crawl through for maintenance. But the major collectors and the cloaca maxima itself were monumental engineering achievements hidden from view. When medieval populations occupied Rome's ruins, many of the smaller sewers fell into disrepair. But the cloaca maxima endured, too large and too essential to abandon. Its massive stone construction resisted decay, its gradient continued functioning, and medieval Romans kept using it even when they'd forgotten who built it or how it worked. Today, you can still see where the cloaca maxima empties into the Tiber. A stone arch opens above the waterline, and in heavy rains, water still pours from that ancient mouth. 2,000 years of continuous service, carrying away what cities prefer not to think about. It's not glamorous engineering. Nobody writes poems about sewers or builds monuments to celebrate waste removal. But it might be the most essential infrastructure Rome ever built. More important than temples, more necessary than amphitheaters. Because cities can exist without entertainment, but they can't exist without sanitation. The cloaca maxima made Rome possible. Everything else, the glory, the empire, the monuments we remember, was built on that foundation. A city that successfully managed its own waste. The Barbagal Mill complex near Arles was an industrial revolution that nobody noticed. 16 water wheels arranged in series down a hillside, each one grinding grain into flour with methodical efficiency. Together, they could process 28 tons of grain per day. That's enough to feed 12,000 people. One installation, running on nothing but flowing water and Roman engineering, mechanizing food production on a scale that wouldn't be matched again until the Industrial Revolution. The genius was in the arrangement. Water from an aqueduct arrived at the top of the hill, channeled into a wooden flume that fed the first water wheel. That will powered millstones that ground grain, but the water itself continued flowing. It dropped to the next level, turned another wheel, ground more grain. Then dropped again, turned another wheel, ground more grain. 16 times this happened, water descending through the complex like a staircase, each step performing useful work. It was cascade engineering, using the same water multiple times before it finally exhausted its potential energy at the bottom. Modern hydroelectric systems use the same principle, extracting maximum work from falling water. The Romans figured it out with wooden wheels and stone millstones. Each wheel was about 7 feet in diameter, positioned to be turned by water flowing beneath it, an undershot design that worked efficiently with a relatively low water flow available. The wheels connected to millstones via wooden gears, transforming the wheel's rotation into the grinding motion needed to crush grain between stones. The millstones themselves were precisely shaped, slightly concave to guide grain from the outer edge toward the center as it was ground progressively finer. Too flat and grain wouldn't flow properly. Too concave and it would grind unevenly. Roman millwrights had perfected the geometry through generations of refinement. Historians still argue whether the Barbagal complex was imperial property, supplying grain to military units, or a private commercial operation selling flour to the surrounding region. The scale suggests imperial backing. Private individuals rarely invested in infrastructure this ambitious. But definitive documentation is lost, leaving us with impressive ruins and educated speculation. Here's what's eccentric about the Barbagal mills. They required constant maintenance, but almost no human labor during operation. Once grain was loaded into the hoppers, gravity and water did everything else. The wheels turned continuously, the millstones ground continuously, and flour poured out continuously into collection bins. Workers would monitor the process, making adjustments, clearing blockages, replacing worn parts. But the actual work of grinding was mechanical, automated in a way that seems startlingly modern. The Roman approach to mechanization was selective. They automated where it made economic sense: large-scale grain milling, water pumping in mines, certain textile operations. But they never developed steam power or sought to replace human labor systematically. Partly this was because enslaved labor was abundant and cheap. Why invent labor-saving machines when labor itself cost almost nothing? But partly it was philosophical. Romans valued tradition, trusted proven methods, and were skeptical of unnecessary innovation. If water wheels worked, why develop steam engines? The question didn't occur to them because the need wasn't pressing. The mills operated for centuries, feeding Auls and the surrounding region through the height of Roman power. When the empire fractured and aqueducts failed, the mills stopped. Without water delivery, the entire system was useless. The wooden wheels rotted, the gears collapsed, the millstones cracked from neglect and weather. By medieval times, the site was abandoned, its purpose forgotten. Farmers plowed fields above the ruins, unaware that industrial machinery lay beneath their feet. Modern archaeology rediscovered the complex in the 20th century, excavating the foundation channels where water wheels once turned. The layout became clear through careful measurement. 16 stations, each with a wheel pit and millstone base, arranged in perfect descending sequence. Archaeologists could calculate the gradient, estimate water flow, and determine grinding capacity. The numbers were staggering. 28 tons per day meant Rome had achieved industrial-scale food processing without anything we'd recognize as industry. No factories, no assembly lines, no mechanized transportation. Just water, stone, and a sophisticated understanding of how to make them work together. The Barbagal mills represent a path not taken. If Rome had continued developing water-powered machinery, expanded the principle to other industries, thought systematically about automation, who knows what might have emerged. Instead, the knowledge remained specialized, limited to specific applications, dependent on infrastructure that proved fragile when the empire weakened. When the mills stopped, the capability vanished. Medieval Europe ground grain in small mills, 1 or 2 wheels per installation, serving local villages. The industrial scale of Barbagal wasn't recreated until much later, when different circumstances drove different innovations. But for a few centuries, in southern Gaul, 16 wheels turned in perfect sequence. Water descended, grain became flour, and Rome demonstrated that mechanization was possible long before the machines we associate with modernity. The wheels are silent now. The channels are dry. But the stones remain, marking where human ingenuity briefly touched something like our own industrial future, then let it slip away into history. The Pont du Gard achieved something that seems impossible. 50,000 tons of stone, stacked 3 tiers high, spanning a river gorge without a single drop of mortar holding it together. Pure friction. Stone on stone, weight on weight, gravity doing all the work of adhesion. And it stood for 2,000 years, surviving floods that washed away modern bridges built beside it. The structure carries an aqueduct channel across the Gardon River Valley, part of the system that brought water to the Roman city of Nîmes. But calling it utilitarian feels like an insult. It's architectural poetry, each arch proportioned with mathematical precision, each stone cut so exactly that the joints between them are nearly invisible. The engineering begins with the foundation. Massive stone blocks rest directly on bedrock, carefully leveled to distribute weight evenly. No deep pilings, no elaborate foundation system, just thorough site preparation and absolute precision in the base layer. From there, the arches rise in 3 tiers. The lowest level spans the river itself, 6 arches carrying the weight of everything above. These arches are huge, each one spanning about 80 feet, high enough that floodwaters pass beneath without threatening the structure. The middle tier has 11 arches, smaller and more numerous, distributing the weight from the top level. And the top tier, the actual aqueduct channel, has 35 small arches, creating a delicate rhythm across the skyline. The progression from few large arches to many small ones isn't decorative. It's structural logic made visible. Each tier responds to different forces, different requirements, and the arch count reflects those needs. The stones themselves tell stories through their surfaces. Marks left by Roman stonemasons are still visible. Inscriptions indicating which crew cut which block, guidelines for placement, even the occasional crude joke carved where supervisors wouldn't see. Some stones show evidence of the lifting process, with holes drilled for the iron tongs that cranes used to position them. These holes were supposed to be filled after construction, but time and budget pressures meant some were left empty. They remain now, tiny windows into the construction process. Historians still argue about exactly how long construction took. Estimates range from 5 to 15 years, depending on assumptions about workforce size and working conditions. The precision required suggests careful, unhurried work. But the Romans were also capable of remarkable speed when motivated. Probably the truth lies somewhere in the middle, methodical but efficient, careful but not obsessive. Here's the eccentric detail. The stones were cut slightly irregular on purpose. Not random irregularity. Calculated variation that created natural-looking surfaces while maintaining perfect structural alignment. The visible faces have a rough texture, but the contact surfaces where stone meets stone are machined flat to within fractions of an inch. This combination of rough exterior and precise interior created a structure that looked organic while performing with mechanical exactness. The aqueduct channel at the top is a marvel of gradient engineering. The water flows at just the right slope, steep enough to maintain movement, shallow enough to prevent erosion. Over the entire length from source to city, about 30 miles, the total drop is only about 40 feet. That's an average gradient of less than 1 foot per mile. Across the Pont du Gard specifically, the drop is about an inch per 300 feet. You can't see it with naked eyes, but the water knew. It flowed exactly as intended, never pooling, never rushing, maintaining steady delivery across the centuries. The structure survived because it was overbuilt. Roman engineers didn't calculate minimum requirements and build to them. They calculated what was necessary, then added margin for uncertainty. The result was infrastructure that could handle forces far beyond normal operating conditions. When floods came, and they did regularly, the Pont du Gard simply endured. Water rose, pressure increased, and the massive stones absorbed the force without shifting. Modern bridges built beside it have been destroyed by floods the Pont du Gard ignores. There's a lesson there about the difference between adequate and excellent. Walking across the top level today, tourists can do this following the ancient water channel. You can see the slight curve built into the structure. The bridge isn't perfectly straight. It has a gentle arc, like a bow drawn taut, that increases structural stability. This curvature helps the bridge resist lateral forces, distributing stress more evenly across the stone. Again, it's physics-made architecture. No mortar means maintenance should be impossible. You can't repair joints that don't exist. But the Romans built so precisely that maintenance was rarely needed. Stones worn by water were replaced occasionally, damaged sections rebuilt after exceptional floods. But the basic structure persisted untouched, doing its job year after year, century after century. When the Roman aqueduct system finally failed, not through structural collapse, but through lack of maintenance during political chaos, the Pont du Gard remained. It became a bridge for carts and pedestrians, then a tourist attraction, then a UNESCO World Heritage Site. The water no longer flows through the channel at the top, but the stones still stand, locked together by nothing but their own weight and the genius of whoever calculated exactly how to cut them. 50,000 tons of proof that sometimes perfect is possible. Trajan's column isn't just art. It's a three-dimensional technical manual, carved in marble, depicting in meticulous detail how Roman military engineering actually worked. 155 scenes spiral up the column shaft, showing 2 military campaigns in sequence. And buried within those scenes, between the battle tableaus and the emperor's appearances, are dozens of engineering vignettes that document construction techniques, siege equipment, bridge building, and fortification methods. It's propaganda, certainly. Every scene glorifies Roman military superiority and Trajan's leadership. But it's also documentation, preserving engineering knowledge in stone at a time when technical manuals were rare and fragile. The column stands over 100 feet tall, a hollow drum of carved marble blocks stacked one atop another. Inside, a spiral staircase winds upward, lit by narrow windows that pierce the outer wall at intervals. The exterior surface is covered completely by the relief frieze, a continuous narrative that wraps around the column 23 times. If you unwrapped it and laid it flat, the frieze would stretch over 600 feet. Walk around the column's base, and you see Roman soldiers constructing a fortified camp. They're digging ditches, erecting palisades, measuring with surveying instruments. The tools are shown clearly. The delabra, a pickaxe-like implement used for digging. The groma for establishing right angles. Measuring rods for maintaining straight lines. These aren't generic representations. They're specific enough that archaeologists have identified actual tool types and construction sequences. Higher up, soldiers build a bridge across the Danube. You can see the pile driver, the timber framework, the stage construction process we discussed earlier. The carved scene shows multiple phases simultaneously. Piles being driven here, beams being positioned there, finished sections already supporting traffic. It's a construction timeline compressed into a single visual space, but the technical details are accurate. Siege engines appear repeatedly. Ballistae positioned outside fortifications. Onagers preparing to fire. Testudo formations advancing under arrow fire. The carvings show not just the machines themselves, but how they were operated. Crews winding springs, loading projectiles, adjusting aim. Historians have used these images to reconstruct Roman artillery, translating carved stone into working replicas. Historians still argue whether the column was intended as engineering documentation or if the technical accuracy was incidental to the artistic and propagandistic goals. Probably both. The sculptors were skilled artists, but they worked from sketches and descriptions provided by people who'd actually campaigned with Trajan. The result is art that happens to be technically accurate because accuracy served the propaganda, showing Rome's military machine in convincing detail. Here's an eccentric aspect. The column was originally topped with a bronze statue of Trajan. Inside the hollow shaft, his ashes were interred in a golden urn. So the column functioned simultaneously as victory monument, technical documentation, and imperial tomb. Multiple purposes layered together, each reinforcing the others. The inscription at the base states that the column's height represents the depth of earth removed to level the site. A hill was excavated to create the forum space where the column stands. Even this detail is engineering documentation, recording the scale of the earth-moving project. Details throughout the frieze show Roman engineering solving problems in real time, building temporary roads through forests, constructing fortified supply depots, creating river crossings under combat conditions. These aren't glorified abstractions. They're specific solutions to specific challenges, preserved because they reflected well on Roman capability. The level of detail varies. Some scenes are crowded and complex, showing dozens of figures engaged in elaborate operations. Others are sparse and symbolic, suggesting action without depicting every element. But consistently, the engineering scenes receive careful attention. Whoever directed the sculptors understood that showing Roman technical prowess was as important as showing Roman military victories. The two were inseparable. Modern engineers and archaeologists study the column like a textbook. When they want to understand how Roman military bridges were actually constructed, they photograph the relevant sections, measure the proportions, analyze the sequences. When reconstructing siege equipment, they refer to the column's depictions to verify other sources. It's become a primary source for Roman military engineering 2,000 years after being carved. The column has survived remarkably intact, though the bronze statue is long gone, replaced eventually with a statue of St. Peter because Rome repurposes even its monuments. The marble surface is weathered, details softened by centuries of rain and pollution. But the scenes remain legible, the engineering documentation still readable to those who know what they're looking at. Standing at the base, looking up at that spiral of carved narrative disappearing into the Roman sky, you're looking at knowledge preserved in the most permanent medium available. Marble doesn't rot like scrolls, doesn't burn like wooden tablets, doesn't crumble like papyrus. It just stands patient and durable, waiting for someone to read what it has to teach. The Romans built monuments to commemorate their achievements, but they also, perhaps unconsciously, built monuments that preserve their knowledge. Trajan's column does both. A victory memorial that's also an engineering manual. Imperial propaganda that's also technical documentation. Art that teaches, stone that speaks, a column that still stands tall, still telling stories of how Rome built its empire one bridge, one road, one fortification at a time. Glass windows changed everything about Roman architecture. Before transparent glass, buildings faced an impossible choice: light or warmth, but never both. Open windows let in sunlight, but also let out heat. Closed windows trapped warmth, but left interiors dark. Then Romans discover how to cast flat glass, and suddenly buildings could have transparent walls. The technique involved pouring molten glass on flat surfaces, usually stone or metal tables, and spreading it while hot. The result was crude by modern standards, full of bubbles and imperfections, with a greenish tint from iron impurities in the sand. But it was transparent enough to admit light while blocking wind. That was revolutionary. Bathhouses were the first major beneficiaries. Remember, baths needed to maintain precise temperatures across multiple rooms. Windows let heat escape, but darkness was intolerable in spaces meant for socializing and relaxation. Glass solved the problem elegantly. Large south-facing windows trapped solar heat, the greenhouse effect, though Romans didn't call it that, while admitting floods of Mediterranean sunlight. The caldarium became dramatically more pleasant when you could see the sky while soaking in near-scalding water. Wealthy villas adopted glass windows enthusiastically. Not everywhere. Glass remained expensive, but strategically placed where light and heat mattered most. Winter dining rooms, for example, where evening meals required illumination but heating was expensive. A glass window oriented toward the setting sun provided both. The glass itself was small, usually no larger than a modern laptop screen. Panes were held in bronze or wooden frames, multiple small pieces creating larger windows. The frames had to accommodate the glass's irregularity. Each pane was slightly different in thickness and shape. Skilled craftsmen would select pieces that fit together reasonably well, filling gaps with putty or resin. Historians still argue whether glass windows were common or remained luxury items throughout the Roman period. Archaeological evidence suggests widespread use in public buildings and wealthy homes by the imperial era, but smaller private dwellings probably made do without. The technology was available, but cost limited adoption to those who could afford it. Here's what's eccentric. Romans understood that different orientations required different window strategies. North-facing windows provided steady light without excessive heat. South-facing windows maximized solar warming in winter. East-facing windows captured morning light. West-facing windows lit afternoon spaces but could overheat in summer. They practiced passive solar design 2 millennia before we coined the term. The glass manufacturing process required specialized knowledge. Sand had to be pure enough. Too many impurities and the glass would be opaque or discolored. The furnace temperature needed precise control. Too cool and the glass wouldn't melt properly, too hot and it would burn and discolor. The casting surface had to be perfectly level and smooth. And the cooling process needed to be gradual to prevent cracking. Each step required skill accumulated across generations of glassmakers. Window glass production concentrated in certain regions, particularly Egypt and Syria, where glassmaking traditions were ancient and sophisticated. Roman expansion incorporated these regional specialties into the empire-wide economy. Glass made in Alexandria might end up in windows in Britain, shipped as prefabricated panes ready for installation. It was early globalized manufacturing with specialized production centers serving distant markets. The military used glass windows in northern provinces where cold weather made them particularly valuable. Forts along Hadrian's Wall had glass windows in commanders' quarters and administrative buildings. Not everywhere. Soldiers and barracks made do with shutters, but strategically, where the investment improved functionality significantly. Glass windows enabled new architectural possibilities. Rooms could be designed assuming natural light would penetrate deep into interior spaces. Covered walkways, like the porticos surrounding courtyards, could be glassed in, creating semi-outdoor spaces usable in poor weather. Libraries and scriptoria benefited enormously from reliable natural light for reading and copying manuscripts. When the Western Empire collapsed, glass window production declined sharply. The specialized knowledge, the trade networks, the wealthy patrons who could afford glass, all disrupted by political fragmentation. Medieval Europe mostly lost the technique for centuries, relying on oiled cloth or thin sheets of horn for translucent, but not transparent, windows. Glass windows didn't return to widespread use until much later, requiring rediscovery and refinement of Roman techniques. But for several centuries, Romans lived with an amenity that wouldn't become common again for 1,000 years. Transparent barriers that admitted light while excluding weather. Solar heating without mechanical systems. Architectural spaces that blurred the boundary between inside and outside. It seems simple now. We take window glass for granted, barely noticing it unless it breaks. But it represented sophisticated understanding of material science and manufacturing. And it changed how Romans experienced their buildings, transforming architecture from massive walls punctured by holes into light-filled spaces where interior and exterior met at transparent boundaries. The sun shining through imperfect greenish glass on marble floors. Light and warmth together. Finally, through Roman ingenuity and sand transformed by fire into something like magic. The cursus publicus was Rome's nervous system, a communication network spanning the entire empire, moving official messages, documents, and occasionally people across thousands of miles with surprising speed. Relay stations every 15 miles, fresh horses waiting, riders changing mounts without stopping for rest. A message from Rome could reach the furthest provinces in weeks instead of months. Information traveled faster than armies, faster than trade goods, faster than rumors. The system gave Rome something unprecedented: real-time control over a continent-spanning empire. The infrastructure was deliberate and expensive. Along every major road, at measured intervals, Romans built mansions, way stations that provided fresh horses, food, lodging, and administrative support. These weren't simple stables, but government facilities staffed by imperial employees who maintained horses, verified credentials, and logged messages passing through. The network employed thousands of people doing nothing but keeping information moving. Only authorized personnel could use the system: governors, military commanders, imperial administrators. Anyone carrying official business received a diploma, essentially a passport that granted access to the relay stations. Without proper documentation, you couldn't claim a fresh horse or lodging. The system was for imperial business only, not available to private citizens no matter how wealthy or influential. This exclusivity made the cursus publicus simultaneously efficient and elitist. Average travel speed on the network was about 50 miles per day. Not impressive by modern standards, but extraordinary for an era when most people walked and 30 miles was a long day's journey. Urgent messages could move faster. Imperial messengers pushing hard could cover 70 or even 80 miles in a day, changing horses every few hours and sleeping only briefly. There are documented cases of messages traveling from Rome to the English Channel in 9 days, covering nearly 1,000 miles. That's over 100 miles per day, sustained across a week of travel through diverse terrain and weather. Historians still argue whether these exceptional speeds were common or represented maximum effort under emergency conditions. Probably the latter. Normal correspondence moved at the standard 50-mile pace, but critical military intelligence or imperial commands received priority treatment with extra resources. Here's an eccentric detail: the relay stations also functioned as intelligence-gathering posts. Staff recorded who passed through, what messages they carried, where they were headed. This information flowed back to Rome, creating a surveillance network disguised as logistics. Governors traveling to new provinces, military movements, even the frequency of messages from particular regions. All of it was monitored and analyzed. The cursus publicus wasn't just communication infrastructure. It was a control mechanism. The road network and the postal system were symbiotic. Good roads made fast communication possible, and fast communication justified maintaining good roads. Messages traveling at 50 miles per day required roads smooth enough for sustained speed. So the cursus publicus created pressure to keep roads repaired, maintained, free of obstacles. Imperial messengers carried weight, literally and politically, and local authorities knew that complaints about poor road conditions would reach Rome quickly. The system required enormous resources to maintain. Thousands of horses, fed and ready for immediate use. Buildings maintained at regular intervals across thousands of miles. Staff paid regular salaries for what might be long periods of inactivity between messages. But the Roman government considered it essential enough to justify the expense. Communication was power, and the cursus publicus gave emperors power over distance. Different message types traveled at different speeds. Routine administrative correspondence moved at standard pace, bundled together for efficiency. Military dispatches received priority, traveling alone with dedicated riders. Imperial edicts moved fastest of all, sometimes with multiple riders carrying duplicate copies in case one was delayed or lost. The system had redundancy built in for the most critical communications. The horses themselves were managed carefully. Not racing horses. Those were too delicate for sustained work, but sturdy animals bred for endurance. Station managers kept detailed records of each horse's condition. ensuring none were overworked. A lame horse could break the chain, so prevention was essential. Fresh horses were constantly being acquired, trained, and rotated through the system. It was livestock management on an imperial scale. Travelers on the system sometimes left graffiti at relay stations, scratch names, dates, destinations, occasional complaints about the food or accommodations. These survive archaeologically, mundane details that humanize the infrastructure. Someone complaining about bad wine at a mancio in Gaul 2,000 years ago, their irritation preserved in stone. When the Western Empire fragmented, the cursus publicus collapsed. New kingdoms couldn't afford the expense, didn't control enough territory to justify it, and sometimes deliberately dismantled stations that represented Roman authority. Communication speeds plummeted. Messages that once took weeks now took months. The medieval world moved slower partly because it lacked the infrastructure that Rome had built to accelerate information flow. Europe wouldn't see comparable postal systems again until the early modern period, when nation-states grew large enough to justify similar investments. But for centuries, Rome had it. A network that moved information faster than travel, that kept the empire connected despite vast distances, that made central control possible across 3 continents. The roads remain, some still carrying traffic. But the mansions are ruins or forgotten, the horses long dead, the system vanished into history. What persists is the memory that it was possible, that ancient civilizations could build infrastructure we associate with modernity, that Rome, 2,000 years ago, had solved the problem of long-distance communication well enough to run an empire. Messages flowing like blood through arteries, keeping the vast body alive and responsive, until the heart stopped beating and the network fell silent. The Romans destroyed mountains to find gold. Not with explosives, they hadn't invented those yet, but with water. Pressurized water, channeled from aqueducts, blasted against hillsides with enough force to liquefy soil and bedrock, washing away millions of cubic meters of earth to expose precious metal veins. The technique was called hushing or hydraulic mining, and nowhere was it employed more dramatically than at Las Medulas in northwestern Spain. The landscape there looks apocalyptic even today. Jagged red pinnacles rising from eroded valleys, entire mountains hollowed out and washed away, leaving only skeletal remains of what once was solid earth. It's beautiful in a devastated way, a monument to human ambition and geological violence. This was Rome's answer to hard rock mining. Why dig when you can wash? The process began with aqueducts, always aqueducts, Rome's favorite infrastructure, built to carry water from mountain streams to the mining site. Not small channels, but substantial waterworks, sometimes hundreds of feet long, capable of delivering millions of gallons daily. The water accumulated in reservoirs above the mining area, held behind dams until enough pressure built up. Then workers would open sluice gates, releasing the accumulated water all at once. The resulting torrent, millions of gallons moving at high speed, hit the hillside like a liquid battering ram. Soil, loose rock, even solid bedrock couldn't withstand the hydraulic pressure. Entire slopes would liquefy, collapsing into muddy slurry that flowed down prepared channels. Gold particles, being denser than surrounding material, would settle in pools and collection points where workers could recover them. The rest, tons and tons of waste, washed away downstream, creating environmental devastation that's still visible 2,000 years later. Historians still argue about the scale of environmental impact and whether Romans cared or even noticed. Evidence suggests they understood cause and effect. Downstream communities complained about sediment choking rivers and agricultural land buried under mining waste. But the complaints were overruled by economic imperatives. Spain's gold funded the empire, and mining continued despite local objections. Here's the eccentric part. Romans sometimes mined underground first, deliberately. They'd tunnel into mountains, creating networks of passages that weakened the internal structure. Then they'd apply hydraulic mining from outside, using water pressure to trigger catastrophic collapse of the already weakened rock. It was controlled demolition on a geological scale, combining tunnel engineering with hydraulic force to achieve destruction neither method could accomplish alone. The tunneling itself was dangerous, claustrophobic work. Enslaved workers and prisoners would excavate by hand, following gold veins through darkness lit only by oil lamps. Once the tunnel network was extensive enough, once enough of the mountain's integrity was compromised, the hydraulic assault would begin. Water would find its way into the tunnels, pressure would build inside the mountain, and eventually the entire structure would fail catastrophically. Imagine standing nearby when that happened. The ground shaking, a sound like thunder, but deeper and sustained. An entire section of mountain collapsing in slow motion as water and gravity combined to liquefy stone. It must have been terrifying and magnificent. The gold recovered justified the effort. Las Medulas alone produced an estimated 5,000 pounds of gold annually at peak operation. That's about $80 million at current prices every year, extracted through nothing but water pressure and human labor. Over 2 centuries of operation, the site may have produced over 1 million pounds of gold total, enough to fund legions, build monuments, and mint the coins that lubricated empire-wide commerce. The engineering required sophisticated understanding of hydrology and geology. Workers had to identify gold-bearing strata, design tunnel networks that would collapse predictably, construct aqueducts that delivered water at necessary volumes and pressures, and build collection systems that separated gold from waste efficiently. Each step required specialized knowledge and careful planning. The water channels had to maintain proper gradient. Too shallow and flow was insufficient. Too steep and erosion would destroy the channels themselves. Collection pools needed the right depth and flow rate to allow gold particles to settle while waste washed through. Even the timing of water releases mattered, coordinated to prevent multiple operations from interfering with each other. The scale of Earth movement staggers the mind. Estimates suggest Las Medulas mining operations displaced over 700 million cubic meters of material. That's enough to bury Manhattan under about 40 feet of dirt. All of it moved by water and gravity, directed by human planning. Modern mining operations use similar hydraulic techniques, though with environmental regulations Romans never faced. The principle remains identical. Use pressurized water to break up and transport material, recovering valuable minerals from the slurry. What's changed is the scale and the concern for ecological consequences. When Roman mining ceased, as imperial priorities shifted and easily accessible gold deposits were exhausted, the devastated landscape remained. No reclamation efforts, no environmental remediation. Just abandoned mines slowly filling with vegetation, red earth exposed to centuries of weathering. The aqueducts collapsed. The reservoirs silted up, the tunnels flooded or collapsed. Nature reclaimed what it could, but the essential damage was permanent. The mountains were gone, washed away in pursuit of gold that's long since been melted down and spent. What remains is the absence, the negative space where mountains used to be. A reminder that engineering serves human purposes for better or worse, and the consequences persist long after the engineers are dust. Rome got its gold. Spain got a scarred landscape and contaminated rivers. Both legacies endure, though only one is celebrated. The hypocaust was invisible comfort. Heat without flames, warmth without smoke, a system so elegant that medieval Europeans would forget how to replicate it for over 1,000 years. It worked through physics so simple that children could understand it. Yet the implementation required engineering sophistication that still impresses modern HVAC specialists. Hot air rises. That's the entire principle. Everything else was just Roman engineers figuring out how to exploit that fundamental fact of nature on an architectural scale. The system started with a furnace, the pre-furnium, positioned outside the building, usually a lower level than the floors it would heat. Enslaved workers fed would continuously into these furnaces, maintaining fires that could never go out. The heat and smoke from combustion had nowhere to go but up and forward, into a space deliberately created beneath the floor. That space, the hypocaust proper, was a hollow area about 2 feet tall, filled with short pillars of brick or stone arranged in a grid pattern. These pillars supported the floor above while allowing hot air and smoke to circulate freely beneath it. The floor itself was typically a thick layer of concrete, heavy enough that it absorbed and stored heat, radiating it upward into the room above for hours after the fire died down. But Romans didn't stop at heated floors. The most sophisticated installations included cavity walls, double walls with a gap between them where hot air could rise. Smoke and heat from the hypocaust would enter these wall cavities through openings at floor level, then rise through the entire height of the wall before exiting through flues hidden in the roof structure. The result was radiant heat from both floor and walls, warming the room without any visible fire, without smoke, without the drafts and uneven heating that open hearths created. Historians still argue whether Romans understood the thermodynamics involved or simply refined the system through trial and error. Evidence suggests they grasped the basics. Hot air rises, dense materials store heat, circulation requires both inlet and outlet. But whether they could have explained convection currents and thermal mass in theoretical terms is uncertain. They didn't need theory to build systems that worked flawlessly. Temperature control was achieved through design rather than mechanical adjustment. Rooms that needed more heat were positioned directly above furnace channels, with thinner floors that transferred warmth more readily. Cooler rooms were farther from heat sources, with thicker floors that insulated against excess temperature. The floor itself could vary in thickness across a single room, creating temperature zones within the same space. It was analog computing again, using architecture to solve problems we now handle with thermostats and forced air. Here's an eccentric detail. Some hypocaust systems included moisture control. Channels built into floors could carry water as well as air, with evaporation adding humidity to otherwise dry heated air. This was particularly valuable in bathhouses, where dry heat could be uncomfortable. Romans experimented with combination systems that delivered both warmth and controlled humidity through the same infrastructure. The efficiency was remarkable. A single furnace could heat multiple large rooms, with heat captured and reused as it traveled through the system. By the time smoke exited through roof flues, most of its thermal energy had been extracted and transferred to the building. Nothing was wasted. Every bit of combustion energy contributed to warming the space. Modern forced air heating systems often lose significant energy through ductwork and poor insulation. Roman hypocausts, by contrast, turned the entire building into a heat exchanger. Maintenance was necessary, but relatively simple. The hollow spaces beneath floors needed periodic cleaning to remove soot accumulation that could restrict airflow. Wall flues occasionally needed sweeping. Romans employed children for this work, since adult chimney sweeps wouldn't exist for centuries. Damaged pili had to be replaced before they failed and allowed floors to collapse. But routine operation required only feeding the furnaces and monitoring to ensure proper airflow. The expense of installation limited hypocaust heating to wealthy homes and public buildings. Excavating beneath floors to create the hollow space, building hundreds of support pili, constructing double walls. All of this added significant cost to construction. But for those who could afford it, the comfort was extraordinary. In northern provinces, where Roman soldiers and administrators faced cold they'd never experienced in Mediterranean climates, hypocaust heating made occupation bearable. Forts along Hadrian's Wall included heated commanders' quarters and bathhouses. Germanic provinces received villa complexes where wealthy Romans could live in warmth despite harsh winters. The technology enabled colonization of regions that would otherwise have been uncomfortably cold for people accustomed to Italian climate. When the empire fractured and technical knowledge dispersed, hypocaust construction largely ceased in western provinces. Medieval builders occasionally discovered hypocaust remains during excavation and misunderstood them completely. Some theories suggested they were underground prisons or mysterious ritual spaces. The idea that Romans had central heating seemed too advanced to believe. It wasn't until the Renaissance that architects began studying Roman ruins seriously. recognizing hypocaust systems for what they were and attempting reconstruction. Even then, full implementation remained rare until modern heating systems developed independently along different technological paths. But for several centuries, Romans enjoyed radiant floor heating, warmed walls, and comfortable indoor temperatures regardless of outdoor weather. They built systems that used passive convection and thermal mass to distribute heat evenly throughout buildings. No blowers, no pumps, no moving parts except smoke rising through carefully designed passages. Just fire below, stone and air above, and physics doing exactly what it does best. Heat rising, comfort spreading, winter defeated through engineering. A warm floor on a cold day. That's civilization. The knowledge didn't die all at once. It eroded slowly, like those Roman roads losing their foundation stones one at a time until the entire structure became impassable. As the Western Empire fragmented through the 5th century, the networks that sustained Roman engineering began failing. Not because people forgot how to cut stone or mix concrete, but because the systems that made large-scale engineering possible, centralized funding, specialized training, empire-wide trade in materials, collapsed under political and economic pressure. First went the aqueducts. These required constant maintenance, regular inspection, immediate repair of any damage. When civic administration broke down, when taxes stopped flowing to Rome and municipal budgets evaporated, the maintenance stopped. Aqueducts that had functioned for centuries suddenly sprouted leaks that nobody fixed. Channels clogged with sediment that nobody cleared. Arches cracked under stress that nobody reinforced. Within a generation, most Western aqueducts had failed. Some were deliberately destroyed by invading armies, cutting water supplies to weaken cities. Others simply fell into disrepair as the knowledge and resources to maintain them vanished. Cities that had enjoyed abundant clean water suddenly faced shortages. Populations declined partly because urban centers couldn't support large numbers without functioning water systems. The baths closed one by one. Not immediately. Some operated for decades after the official fall of Rome in 476. But without aqueducts delivering millions of gallons daily, without the economic surplus to maintain furnaces and pay staff, without the social structures that made public bathing culturally central, the great bath complexes became too expensive to operate. They were abandoned, then quarried for building materials, their sophisticated hypocaust systems buried and forgotten. Medieval Europeans would occasionally discover them during construction and have no idea what they'd found. The roads lasted longer. Roman road construction was so overbuilt that even without maintenance, the roads remained passable for centuries. But gradually, without repair, they deteriorated. Surface stones were pried up for other construction projects. Drainage ditches filled with debris, allowing water to undermine foundations. Trees grew through cracks, their roots destroying the careful layering. By the medieval period, many Roman roads were still visible and sometimes used, but their original quality was lost. They'd become paths rather than highways, adequate for local travel, but no longer capable of moving armies at Roman speeds. Concrete technology survived longest in the East. Constantinople maintained Roman building techniques, continuing to construct with hydraulic cement and sophisticated engineering. But in Western Europe, the recipe for true Roman concrete was lost. Medieval builders used lime mortar, adequate for many purposes but nowhere near as durable as Roman concrete. When they encountered ancient structures built with pozzolana concrete, they couldn't replicate them. The Pantheon's dome remained the largest in the world for over a millennium, partly because nobody knew how to build something comparable. Historians still argue about why the knowledge disappeared so completely. Some emphasize the breakdown of trade networks that supplied specialized materials like pozzolana. Others point to the collapse of specialized education. No more schools training engineers. No more transmission of technical knowledge across generations. Still others suggest that changing economic conditions made large-scale construction economically unfeasible, so the knowledge atrophied from disuse rather than being actively lost. Probably all these factors combined. But the result was clear. By 600 CE, Western Europe had largely forgotten how Romans built their greatest structures. The siege engines went first. Complex torsion artillery required specialized knowledge to build and maintain. The mathematical formulas relating projectile weight to spring dimensions were written down in only a few technical manuals, and when those manuscripts were lost or stopped being copied, the knowledge vanished. Medieval siege weapons were cruder, trebuchets, and catapults that worked through simpler mechanical principles. Effective, but not as sophisticated as Roman ballistic calculators had been. Surveying skills declined sharply. The instruments, the groma, the chorobates, survived in some places, but the systematic methods of using them, the accumulated knowledge of how to survey large construction projects accurately, became rare. Medieval builders could construct impressive cathedrals, but they did it through different techniques, relying more on geometric rules of thumb than precise surveying. Even literacy patterns contributed to knowledge loss. Roman technical manuals were written for a literate administrative class that largely disappeared. Medieval literacy concentrated in monasteries, where monks copied religious texts but often ignored technical works they couldn't understand or didn't value. Vitruvius survived, barely, in a handful of copies. Other engineering texts vanished completely, leaving only fragments quoted in other works. Here's what's melancholy about the decline. It was reversible. The knowledge wasn't inherently lost. It was written down, built into structures, potentially recoverable through study and practice. But the social conditions for recovery didn't exist for centuries. Europe was busy surviving, defending against invasions, reorganizing politically. Large-scale infrastructure projects seemed impossibly ambitious when local authorities struggled to maintain basic security. The Eastern Empire, Byzantium, kept much of the knowledge alive. They continued building with Roman techniques, maintaining aqueducts, constructing with concrete. Islamic civilization, expanding through former Roman territories, recovered and built upon Roman engineering knowledge, combining it with innovations from Persia and India. But in Western Europe, the Roman engineering tradition went dormant. It slept through centuries of political fragmentation, waiting for social conditions that would make ambitious infrastructure feasible again. When the Renaissance arrived, Europeans rediscovered their Roman heritage with something like shock. They excavated ruins, studied proportions, tried to decode building techniques. The knowledge returned slowly, imperfectly, often misunderstood. But it returned. Engineers learned to survey again, to calculate loads, to build aqueducts and bridges using principles Romans had known. The long medieval sleep ended, and engineering woke up, remembering old lessons and adding new innovations. But the centuries between were real. The knowledge was genuinely lost, recovered only through archaeological study and Renaissance scholarship. Rome's greatest engineering achievements became mysterious, their construction methods debated, their sophistication surprising even to educated people. We're still learning from them, still discovering techniques we'd forgotten, still occasionally finding that Roman solutions were better than modern ones for certain problems. The knowledge declined, but never completely disappeared. It waited, patient as stone, for people ready to learn again. Stand in front of any modern dam, and you're looking at Roman geometry. The curved wall that holds back water uses the same principle as those arched aqueduct bridges. Lateral forces converted to compression, weight distributed through shape rather than just mass. We added steel reinforcement and computer modeling, but the fundamental insight is ancient. Walk through a modern city's storm sewer system, and you're in the descendants of the Cloaca Maxima. The hierarchy of small drains feeding into larger collectors feeding into main channels. The careful gradient that moves water without eroding infrastructure. Even the arched ceilings that distribute load. All of it echoes Roman solutions to eternal problems. Today, civil engineers study Roman roads during their training, not as historical curiosities, but as functioning examples of how layered construction distributes stress. The Statumen, Rudis, and Nucleus system appears in modern highway design, translated into new materials but preserving the ancient logic. When we build roads to last 50 years, were aiming lower than Romans did accidentally. Concrete chemistry has come full circle in surprising ways. For decades, modern Portland cement was considered superior to Roman concrete in every way: stronger, faster setting, more predictable. Then marine biologists studying ancient harbors noticed something peculiar. The Roman concrete was still getting stronger, still generating new crystalline structures, still defying the degradation that destroys modern concrete within a human lifetime. Scientists began reverse engineering the Roman formula, analyzing samples from underwater structures, recreating the volcanic ash mixtures in laboratories. What they found was humbling. Romans had stumbled onto, or deliberately created, a concrete formula that modern material science is only now beginning to match for durability. Some contemporary engineers are seriously proposing a return to Roman-style concrete for certain applications, particularly marine construction, where longevity matters more than initial strength. The Pantheon's dome remains the world's largest unreinforced concrete dome. Every modern attempt to build something similar requires steel reinforcement, computer-aided stress analysis, and materials Romans never dreamed of. Yet the ancient structure stands, having survived earthquakes that destroyed buildings around it, outlasting empires and ideologies and technological revolutions. When structural engineers study why it hasn't fallen, they find sophisticated load distribution, invisible tension rings, clever use of progressively lighter materials, a complete understanding of how domes want to fail and how to prevent that failure. The knowledge was there 2,000 years ago, built into stone and concrete, waiting for us to notice. Historians still argue about how much of Roman engineering was theoretical knowledge versus empirical refinement. Did they understand stress analysis mathematically, or did they just know what worked through trial and error across generations? The answer probably varies by specialty and era. But what's undeniable is that their solutions were correct. Not approximately correct, not adequate for their time, but genuinely optimal in ways that remain relevant millennia later. Modern bridge engineering borrows Roman arch principles constantly. The way loads transfer through voussoirs to abutments, the relationship between span and rise, the strategic use of multiple arches rather than single massive spans. These remain foundational concepts taught to every civil engineering student. We've added cables and steel trusses and computer modeling, but we haven't replaced the arch. We've supplemented it because the Roman solution to spanning empty space was too elegant to improve upon fundamentally. Passive solar design in contemporary architecture often rediscovers Roman window strategies. South-facing glass to capture winter heat, carefully calculated overhangs to block summer sun, thermal mass to store and release warmth gradually. These principles appear in modern sustainable building manuals as innovations, though Romans practiced them routinely in bathhouses and villas. We lost the knowledge, then rediscovered it as if it were new, when really we were just remembering. The lesson of Roman engineering isn't that ancient people were smarter than us. They weren't. They had less accumulated knowledge, cruder mathematics, more limited theoretical understanding. But they had time. They had patience to observe how structures behaved across generations, to refine solutions incrementally, to build things meant to outlast their builders by centuries. Modern engineering often optimizes for cost and construction speed, building to minimum necessary standards because replacing infrastructure in 50 years seems acceptable. Roman engineers built to maximum achievable standards because permanence was valuable in itself. Their buildings were meant to announce Rome's eternal presence, to outlast enemies and prove superiority through sheer durability. That cultural value system produced infrastructure that's still teaching us lessons 2,000 years later. The greatest Roman engineering achievement wasn't any single structure. It was the system, the way they approached large-scale problems methodically, applied solutions consistently across vast territories, trained generations of engineers who built on inherited knowledge rather than starting over. They created an engineering tradition, not just individual monuments. And that tradition, though interrupted and partially lost, eventually resumed. Renaissance architects studied Roman ruins. Enlightenment engineers rediscovered Roman techniques. Modern builders incorporate Roman principles. The knowledge moves through time unevenly, sometimes lost, sometimes rediscovered, but persistently valuable because it addresses permanent problems of how to build things that endure. Tonight you've traveled through Roman infrastructure, from mountain springs carried to cities by invisible aqueducts, through sewers large enough to boat through, past water wheels grinding grain without human labor, across rivers on bridges built in days, beneath dome ceilings that shouldn't be possible but are. You've seen engineering that served empire, warfare, vanity, necessity, and sometimes just the pure challenge of solving difficult problems elegantly. The structures remain, weathered, ruined, occasionally still functioning, testifying to choices made by people whose names we've mostly forgotten. They built with stone and concrete, sweat and mathematics, ambition and patience. They built for forever, and sometimes they succeeded. The roads stretch on through darkness. The aqueducts carry memory instead of water, and the engineering endures, waiting to teach anyone willing to stop and learn from stones that have outlasted empires. Rest now in the knowledge that humans can build things that last. That careful thought and patient work can create beauty and function that transcends the builder's mortality. That somewhere tonight, water flows through Roman channels, traffic crosses Roman roads, and tourists stand beneath the Pantheon's dome, gazing up at an oculus that's framed Mediterranean sky for 2 millennia. Engineering as a form of hope, permanence, defiance of entropy. Rome understood that and built accordingly. Their gift to us is proof that it's possible. That ambitious infrastructure, carefully designed and solidly built, can outlast everything except time itself, and sometimes even that becomes negotiable. Let that thought settle as gently as sediment in an aqueduct channel, as firmly as foundation stones beneath a road, as permanently as concrete growing stronger beneath ancient harbors. The engineers are gone, but the engineering remains, speaking in stone about patience and permanence, teaching lessons across centuries to anyone willing to listen to what silence has to say. Sleep while knowing that good work endures, that solving problems elegantly matters, that building things to last is an act of hope that sometimes, just sometimes, proves justified by centuries of persistence. The Roman engineers have been dust for 2,000 years, but their roads still carry traffic toward futures they couldn't imagine, and that's a kind of immortality worth achieving, a legacy worth leaving, a dream worth building stone by patient stone. Sweet dreams.